This production is brought to you by the University of Edinburgh.
Okay, morning everyone. So we're going to carry on from where we were yesterday. So if anyone wasn't here yesterday, I recommend that you'll have to study the notes in some detail. I'll give a very quick revision though. So we finished off power and energy, and we did discuss in detail about how you do some of those calculations. So I think that conversation was very useful with all the questions being asked. We then moved on to developing the complex Fourier series, which is developed because it's mathematically more tractable than the trigonometric Fourier series, and also because it will help us develop the Fourier transform, which is a tool which we're going to use to analyze non-periodic signals of infinite duration in continuous time. Just as a recap, the way we develop the complex Fourier series is to introduce this idea of a complex signal. So the complex signal has two terms. You can almost consider it as a multi-channel term. It could be a multi-channel signal, and it's got a real part and it's got an imaginary part. So the complex phasor is the sum of those two, and you can view it as a point which moves around in a two-dimensional space as a function of time, or if you were to plot the signal in basically 3 dimensions, it will be like a coil. Some people call it a corkscrew, but maybe a coil is more appropriate for electrical engineers. Now you might say, how does this signal physically exist in practice? Anyone want to make suggestions of how possibly a complex signal could exist in practice? Go on. One thing maybe to help sort of trigger an idea is to note that the real part, the imaginary part, are essentially orthogonal to each other. You can't represent the imaginary part with the j term in terms of the real part because it's got the j. So exactly, yeah. So if you've got an electromagnetic wave, you've got the electric field and you've got the magnetic field, and they're essentially orthogonal. And it is possible, basically you can view that as a complex phasor. You might want to, you can take up the details of that with your EM lecturer, but I think that's a good analogy for a complex signal. And in fact, all of communications, since radio signals are EM signals, electromagnetic signals, then actually a complex phasor, A e to the j omega naught t, is actually quite a natural way of representing communication signals. So this is going to come up a lot, probably more in the third year than in the second year, but you will meet this. So once you've introduced this idea of a complex phasor, which you can try and have a physical analog with, or you can just accept it's a mathematical model, because at the end of the day, we use mathematics to try and model the observations we've got, and as long as it models the observations really well, that could be considered sufficient. There's a bit of philosophy of science there, but so that would be a good model. So the way you develop the complex Fourier series from a trigonometric Fourier series is to use the fact that you can express a cosine and a sine as a linear combination of complex phasors which are going in opposite directions. So you can have one with a positive frequency and one with a negative frequency. The linear combination of those two gives either a cos or gives a sine. And then you can, in the trigonometric Fourier series, which would have been here, this would have been a cos, but you replace it by its complex equivalent, and that would have been the sine. You replace it by that identity there. And basically we steadily went through some derivations where we did lots of rearrangements. Yeah, there's a process that I do for these manipulations, which is always a 3-step process. All the time we come across that process, and it's basically 3 R's. I'll write it down when we actually do an example. And it's basically, you start off with something, you replace something in the formula. So we've replaced the sine and the cos. You then basically rearrange or reorganize something. And then the final stage is you can basically recombine or recognize a simplification. So you basically replace something with a substitution, you rearrange something, and then you recognize something that's simplified. And as we went through that, and I'll just jump to here, we came out with this expression at the end, a single summation over all complex phasors of all frequencies. So we can now represent a signal x of t as a linear combination of these complex phasors the frequency of these phasors is omega naught is integer, and so the frequency of the phasor e to the j in omega naught t is the nth multiple of a fundamental frequency, because it's at n omega naught. And the coefficients x of n are in general complex. So now they're complex numbers. So these coefficients have magnitude and phase. And I think in the first lecture I said that you'll need to be familiar with complex numbers. And basically this is why, because we're going to need them. So this is a very compact and actually quite elegant expression. So if we went back to handout number 1, that's our trigonometric Fourier series. So the question is, do you prefer that one over our new expression, which is much simpler? I don't know. Choices. One of the things is, that diagram sort of pushed off the bottom, I haven't had a chance to fix it. One of it is if you want to work out the Fourier coefficients x of n, then you'll see it's just a single integral. So when you do trigonometric Fourier series, you have to do 2 integrals to get the a's and the b's. Complex Fourier series, you just do a single integral. It's an integral over any period. So we had a long conversation yesterday about a periodic signal. You can choose any period to do this integration over. So depending on your signal, you may or may not want to pick a sensible region, which just makes the maths easier. So x of n is 1 over the period, integral over any period of a signal multiplied by e to the minus j in omega naught t. So notice the fact that in the what I'll call the inverse Fourier series, effectively, where you go from the Fourier coefficients to the signal, it's at e to the plus j in omega naught t. Whereas when you go from the signal to the Fourier coefficients, you've got an e to the minus j in omega naught t. When we get onto Fourier transforms, we're going to see a very elegant symmetry between these formula, which will become much clearer. And one of the things, reason this symmetry exists is because the time domain is no more important than being in a frequency domain. There's a one-to-one mapping between the two, and depending, as I said a couple of lectures ago, depending whether you come from the physicist's world where you might prefer to be in a frequency domain because it makes sense to analyze the spectra of your observations, or whether you're an engineer and you come from a time domain and it makes more sense to analyze the time domain signals because that's what we do, then there should be an equivalence. One is no more important than the other, and that we'll see a symmetry which is just really elegant. This formula here I haven't derived. I'll leave it as an exercise for you to do. So how on earth do you derive this? This formula is really easy to derive, and where it comes from is by using basically this notation here at the end. So the complex coefficients can be written in terms of the real coefficients, the trigonometric coefficients, as an minus jbn divided by 2. So all you need to do is to substitute your calculation for an and bn into this equation here. Now if you remember, the calculation for an was something like 1 over t, integral of x of t cos n omega naught t. And then you put in bn, 1 over t integral x of t sine n omega naught t. So you replace, you rearrange, so you will group the cos and the sine terms together, because it will be x of t cos n omega naught t minus j sine n omega naught t, and we all know that cos minus j sine is equal to e to the minus j times whatever it is. Okay, so in fact, whilst it's not in the handout, you could derive that, and well worth doing. Yeah.
Is there going to be a case that the regular Fourier series is going to be prepared from the complex Fourier series, or vice versa, apart from the maths of it?
Yes, occasionally yes. So one example would be, I think, if you've got a very specific signal, I think if you've got a real signal and it's even, so it only consists of cosine terms, then you might prefer to evaluate the trigonometric Fourier series because you know all the sine terms are equal to 0. And I think this is used in some forms of audio coding. It's something called the Discrete-cosine transform. So the Fourier series effectively reduces to the cosine transform when you know it's odd and even. So there are some cases where, for computational efficiency, you might prefer it. However, we're converting to the complex Fourier series for 2 reasons. One is because it gives us a theoretical framework to go beyond Fourier series to develop the Fourier transform, and it's slightly more general. It's completely equivalent because all we've done is just replace cosines and sines by complex phasors. But it can just make some mathematical analysis slightly easier. Okay, but it's a good question. Yeah, but I think this discrete cosine transform is an important one.
This production is copyright the University of Edinburgh.